Okay, welcome to video number 19 of the Diaries of a Coronavirologist YouTube channel. Today is the 4th of May. May the 4th be with you. And we're up to about 3.6 million, just under 3.6 million confirmed cases of COVID-19 and about 251,000 confirmed deaths. So today's video is a bit different, as the timestamp may have alluded to. It's a lot longer than normal. For those who watch the channel frequently, you may remember me talking last week about the fact I had a few larger presentations going on. For those who don't watch the channel frequently, last week I had a few bigger presentations going on. So the first of those was on Monday, where I did a joint presentation with my PhD supervisor for the department I did my PhD in. That was recorded and posted to the department's Vimeo page, and I've put a link for that down in the description to this video. The other talk was for Brewing Up Science, which I think is a great initiative put together by Jackie Lovett. So here in Baltimore, Jackie has been organising presentations, TED-style talks from local scientists hosted by local breweries. So kind of somewhat informal presentations. They're usually done with the presenter having a beer in their hand, or at least resting on the table where the laptop is resting for the slides. But it's a slide-based presentation for an audience of all kind of disciplines, be that science or not. So with the lockdown and all the things that we're going through now, Jackie decided to put together another Brewing Up Science, this time a virtual one, and she invited me to be the speaker. So I did one back in November, actually out at a brewery, and this was me doing a virtual one. So it was an honour to be the first person to speak twice at Brewing Up Science. We recorded that through the Zoom that we did, and that's what I've attached to this video here. So there may be a few issues with the sound in places. Apologies. It's all getting used to these new systems and working out how they all work. I think most of the talk's there though. We did have to go through a few edits and things like that to try and get it all working. So hopefully it's mostly there. Now the way that's set up is I've done about a 20-minute, it's about 25 minutes worth of slides that I run through talking about all of the SARS-2 COVID-19 pandemic things, and then talking about the work that we're doing in the lab, or some of the work we're doing. So it's kind of all things I've talked about on the channel before, but all put together into one presentation. I then do a chunk of Q&A at the end. I feel like that was possibly one of the more valuable parts of it, to sort of really directly tackle the questions people had. I've done timestamps down in the description as always, so if you don't want to watch the whole presentation, you just want to do the questions, you can skip to that, or if you don't want to do the questions, there'll be a timestamp for when those start. Doing those questions though did give me an idea regarding the channel, because a lot of people are asking interesting questions and each time I post a video, which is awesome, so thank you. But I'm being very slow at getting around to answering them, finding the time to put into writing out an answer in the comments. So I started to think that maybe I should tackle them in videos. So I thought I would ask people, is that a good idea? And how would you prefer it done? If so, please leave comments down in the comment section. So my thoughts are either I compile all the questions for 3 videos or so and then do one video tackling all the questions, so various different topics, or I just do a little question section each time I post a video. So obviously that would extend the videos from sort of that 5 to 10 minutes or whatever I'm doing now to maybe 5 minutes longer, so that I can do some questions, but it may allow them to be more relevant to the video I've just posted. Anyway, if you think it's an idea that would add value to this channel, or if you think it's a terrible idea and I shouldn't do it, please leave comments down below and I will look through them and work out what I intend to do. Anyway, with all that said, I will now transition into a slide deck. Like I say, hopefully all of the sound worked well enough and it's all clear. Something a little bit different and a bit longer if people want something more long form. Anyway, as always, please stay safe, wash your hands, don't inject bleach. Since we're having to say silly things like that, don't run with scissors either. And please keep calm and carry on. We will get through this. Thanks for tuning in, as always. Okay, so we're just getting past 7 o'clock, so I figure I'll get us started. And as people filter in, hopefully they can just pick up with wherever we have got to. So I'm Stuart. I'm a postdoctoral research scientist at the University of Maryland School of Medicine, and I work in Matthew Freeman's lab, where we study coronaviruses, which is why Jackie has asked me to give this the inaugural virtual Brewing Up Science session. So before we get into things, I just want to say a massive thank you to Jackie and Brewing Up Science for putting this session and all the other ones together. This is actually my second presentation for Brewing Up Science, the first one being back in November, and I'll come back to that, but it's an honour to be the first returning speaker for Brewing Up Science. I also want to say a big thank you to all of our co-hosting breweries and distillery tonight. These are tough economic times for everyone, and so if you can, please go and support these places. They're all doing pickup, and I think some of them are doing delivery. So if you can spare an order, please shoot one the way of one of these wonderful places. And once everything opens back up, I for one can't wait to go and have a beer at these fine drinking establishments. Tonight I'm drinking a lovely tipple from Ministry of Brewing, so thank you for that. Sorry everyone else, I love you all equally, but Ministry got my vote for my drink for this presentation. So to just give a little overview of what I intend to do with this time we have tonight on Zoom, I'd like to give a very general background into coronaviruses and then focus very heavily on an overview of the SARS-2 outbreak. So what's been going on in this outbreak, a little reminder of everything that's been happening, to hopefully tackle some of the bigger and broader questions. I'll then tell you a little bit about the work we've been doing in the lab, the kind of thing we're focusing on here at the School of Medicine, and then I'll hopefully have plenty of time at the end to do Q&A because I feel that may be the most value from this session. So as I said, this is my second presentation for Brewing Up Science, and my last one was back in November at Monument City, where I introduced coronaviruses with a picture of a bottle of Corona. And I made a comment somewhere along the lines of, these viruses don't have anything to do with this weak Mexican beer that doesn't hold a candle to the quality of beer you can buy at the bar here. The same is true for all of our co-host breweries tonight. But I think now everyone is well aware that these are viruses that can cause significant human disease. So we now know there are 7 human coronaviruses, and they can be broadly divided down into 2 categories of low pathogenicity and high pathogenicity coronaviruses. So the low pathogenicity viruses have the catchy names of HCoV for human coronavirus, 229E, OC43, NL63, and HKU1. And these viruses cause common colds. So every winter when you get that common cold where you run down and you've got a blocked up nose, maybe a bit of a sore throat, maybe a bit of a headache, but nothing too severe, 10 to 40% of those common colds are caused by these common coronaviruses, by these low pathogenicity coronaviruses. Now those viruses don't garner too much research interest. The coronaviruses that do, especially now, are the high pathogenicity coronaviruses. So to take these chronologically, these are SARS coronavirus, possibly SARS coronavirus 1, I should say now, MERS coronavirus, and SARS coronavirus 2. And I'll tackle each one of those in a bit more detail over the next couple of slides. But I just want to bring up this phylogenetic tree of coronaviruses to give a little bit more background on how coronaviruses relate to one another. So a phylogenetic tree is just the evolutionary relationships between different things. So here it's the evolutionary relationship between different coronaviruses. The closer things are to each other in this diagram, the more closely they are related. So for example, down in the bottom right-hand corner, 229E and NL63 are very closely related to each other and much more distantly related to HKU1 and OC43 on the left-hand side. SARS-2 sits somewhere around here, being very close to SARS-1. The two are about 80% identical at a genetic level. Now, the other reason I want to show you this phylogeny is to point out that there are, on this diagram from a few years ago, a lot of bat coronaviruses. So all the viruses that have BT at the front are bat coronaviruses. So we've been aware that there are a lot of coronaviruses in bats, and we know that a lot of those coronaviruses have potential to infect humans, or at least infect human cells in a lab setting. And this to have been a common feature for the high pathogenicity coronaviruses in that they seem to have an origin in bats. So the first high pathogenicity coronavirus to emerge in the human population was SARS. So this is severe acute respiratory syndrome coronavirus, and it came from bats. So not only is this virus similarly named to the current virus that is causing the pandemic, there are a lot of similarities in the way it came into the human population. So we know for SARS-1 that this virus originated in bats, and that virus from bats was able to infect palm civet cats, which were being sold in wet food markets in the Guangdong province of China. From here, they were bought by humans, and the virus was able to transmit from palm civet cats into humans and then spread between humans. Within a matter of months, this virus spread around the world. So in about the 8 months it was circulating, there were over 8,000 cases and close to 800 deaths, meaning about 10% of the people who contracted this virus died from it. Fortunately, we were able to stop this virus outbreak with public health intervention. I think it's pretty clear now that we don't have any vaccination or antiviral therapies for coronaviruses. And SARS wasn't stopped by these. SARS-1 wasn't stopped by these. It was stopped by the measures of public health intervention, such as quarantine, amongst other factors that maybe we can talk about in the Q&A if people want more detail. But what SARS demonstrated was this idea that coronaviruses could spill over from bats into the human population. You could get these zoonotic events. So zoonosis is the transmission of an animal virus into the human population. And we got more evidence of this happening in 2002 when another highly pathogenic human coronavirus was found. And this is MERS, Middle East Respiratory Syndrome coronavirus. So once again, MERS originated in bats and transmitted into the human population via an intermediate host. This time that intermediate host was camels. So this virus, fortunately, does not spread very well between humans. And most cases have been largely confined to the Middle East and particularly the Kingdom of Saudi Arabia, where there's much closer contact between humans and camels. So a lot of cases, it's someone who's come into close contact with a camel who then doesn't spread that virus any further. So in the 8 years that this virus has been infecting humans, there are still sporadic cases occurring. There's only been about 2,500 infections. However, there have been about 35% of those people have died, which places this as one of the most lethal human viruses we know. So it's good that it doesn't spread well. But again, this really raises the fear of coronaviruses that could spill over from bats into humans. And there's always a fear that something that's as lethal as MERS and as transmissible as SARS could make its way into the human population. So there were fears of this before it happened, and now it has. Thankfully, this virus is nowhere near as lethal as MERS, as I'll sort of come to talk a little bit more about shortly. I just want to go briefly over the naming. So I've been calling it SARS coronavirus 2, SARS-2, and this is the official designation that's been given by the ICTV. So this is the International Committee for the Taxonomy of Viruses. Initially, though, this virus was being referred to as the Wuhan coronavirus, colloquially. Slightly more officially, it was being called the 2019 nCoV for novel coronavirus. In the press, it's still sometimes being referred to as the coronavirus, but hopefully I've made it clear to you that this is a bit of a misnomer because there's a lot of other coronaviruses out there. The WHO call the virus that causes COVID-19. So this is the disease, coronavirus disease 2019, not the 19th coronavirus. So we kind of have a naming structure similar to HIV and AIDS, for example, where HIV is the virus that causes AIDS. Here, SARS coronavirus 2 is the virus that causes COVID-19. And as I've been strongly alluding to, this virus originated in bats. So the closest relative virus we know is a bat coronavirus called RATG13-2013 because it was discovered in 2013. And this is about 96% identical to SARS-2. Now, while this is very closely related to SARS-2, it is not the direct ancestor for the human virus. as this amount of the genetic difference in coronaviruses represents somewhere between 25 and 65 years of evolutionary divergence. So we don't yet know the direct ancestor of SARS-2. The rat G13 and SARS coronavirus 1 have common ancestors of SARS-CoV-2, being that they are closely related, but they are not direct ancestors in the same way that chimpanzees and humans have common ancestry but are not evolved from one another. We also don't know the intermediate host for this virus, or if there even is one. So as I was discussing with SARS-1 and MERS, there were intermediate hosts in the transmission into the human population of palm civets and camels. And we don't know if that was the case for this virus, and I'll expand on that in a moment. We also don't even know what the first case of this virus was. We don't know when the first human infections were occurring, but we do know when the first case was reported, which was back on the 30th of December 2019. So this was a patient in China who developed pneumonia of unknown cause. While this is the first reported case, it seems clear by now that the first cases were probably occurring in November, if not earlier. Some estimations suggest that the first cases, or the earliest cases, may have been back in September 2019. But it was on the 30th of December that the first case was reported. A day later, it became clear that this was actually a bigger problem than initially realised, when it became clear that there were 27 people who all had this pneumonia of unknown cause, that all had connections to the Hunan seafood market in Wuhan. At this stage, the WHO were alerted because there was a clear link between all of these patients with this pneumonia. On the 1st of January, Chinese authorities moved in and closed down the Wuhan seafood market and totally disinfected it. Now, this was a great attempt to try and stop further spread of this pneumonia from something in the market. But it does mean that if there was an animal source, any evidence of that was destroyed. However, as we've learned more about this outbreak and the timeline of it all, it's become more and more clear that there may have been cases before this initial burst connected to the seafood market. So it's possible there wasn't an animal source there, but if there was, evidence of that was destroyed. Now, on the 3rd of January was when I read my first news article about this outbreak. And I still very vividly remember reading this BBC News article lying in bed on Friday morning before I came into work. The Saturday after that, the 4th of January, I also vividly remember going for a walk with my now girlfriend and telling her about the history of the SARS-1 outbreak. Yes, I am that sort of person. And I ended that story by saying that there's now a mystery virus that's caused 44 cases of pneumonia in China, which is kind of interesting because it sounds very similar to SARS. But it probably won't be a big thing. That was what I said at the end. And clearly I got that one very wrong. So on the 7th of January, it became clear that we were dealing with a coronavirus. And by the 11th, the genome sequence was published online, so we could all see what we were dealing with. So at this stage, we knew we had a novel coronavirus. The conversation then shifted to being in the lab, where, again, another vivid memory from those early stages was talking to my boss, and the two of us saying something along the lines of, people are going to jump on this and get excited, but it probably won't be a big deal, so let's not go with it. Working with high containment pathogens is a pain, so let's not get too carried away. So obviously we got that one wrong as well. I got it wrong twice. But it rapidly became clear that this was going to be a bigger deal than we might have initially speculated. So the first case outside of China was reported on the 14th of January. By the 20th of January, we had the first case here in the USA, and the first case back from where I'm from, the UK, was on the 31st of January. So this virus started to rapidly spread around the world throughout January. At that time, though, a lot of those cases were still being associated with travel to China. And indeed, that was definitely the case for this first reported case in the United States. So this was a businessman who had traveled to Wuhan, came back to Washington State and developed symptoms of COVID-19. So samples were collected from that patient and sent to the CDC, who were able to grow up the SARS-2 coronavirus, and they sent that to us, and it arrived here on the 7th of February. We were amongst the first 3 labs in the country to receive samples of this virus, I believe. Wait for some approvals to go through before we could start working with the virus appropriately. And so on the 10th of February, I started making our lab stock of the virus so that we'd have more to work with. On the 15th of February, one of the more surreal moments of my life occurred, where my back appeared on the front page of the Washington Post. And since there, things have just expanded. So the first death on US soil came on the 29th of February. By the 11th of March, the WHO finally declared this a pandemic. And by the end of March, a third of humanity was under some form of lockdown. And obviously, we are still all suffering from those lockdown measures, hence why I'm talking to you through a Zoom conversation instead of at one of our fine co-hosting breweries. From the 1st of April, we hit 1 million cases. 2 weeks later, we passed 2 million cases. And a little bit under 2 weeks after that, this week, we crossed 3 million cases. So we really have started to hit this exponential growth curve. Right now, we're sat around 3.2 million cases with just a little bit under 230,000 deaths, which represents a case fatality rate of about 7%. So this is the number of deaths divided by the total number of cases. Now, I suspect that this case fatality rate won't be the true number when all is said and done. I don't think this virus is killing 7% of the people it infects, because I think that we are underestimating the total number of cases because we've had many issues with testing. So I think there's significantly more undiagnosed or unregistered cases. So therefore, I think the case fatality rate is probably lower because we're probably doing a very good job of detecting the deaths, but not the mild cases. So this is just a picture of the world, which potentially is being skewed by where it's doing the most testing. And this is just an image of what's going on in the United States. So there's been around 1 million cases and about 61,000 deaths, which is a case fatality rate around 6%. So slightly lower than the global average. The US seems to be handling at least the case fatality rate much better than the UK, which I was sort of surprised to see how different the two were. In the UK, the case fatality rate is around 13%, which is somewhat worrying. But maybe that's more to do with the testing. Again, I haven't looked into it too much. But interestingly, the UK, where I'm from, and the US, where I live, have tracked pretty similarly in the way they responded to this outbreak. So this is just a graph looking at how cases have grown since the 100th case was confirmed. And you can see that the UK and the US were doubling their number of cases roughly every 3 days. Both have now seemingly started to plateau, though, which is good news. Other countries, though, such as South Korea and New Zealand, seem to have handled this much better, hitting those plateaus much earlier and therefore controlling this much better. So I just wanted to highlight the fact that some places have dealt with this better, which gives hope for dealing with this in the future, if we have to again, for some lessons that could potentially be learned. So just to briefly touch on the disease, because I'm thinking most people are probably well aware of the major symptoms of COVID, but just to go over it. The main symptoms are fever, a dry cough, and shortness of breath. And obviously things like fatigue that are associated with that. Recently, the CDC added a few extra symptoms to their major classifications for COVID-19, such as the loss of sense of taste and smell, having chills and repeated chills, and sore throat. So the symptom list has expanded as we've got more and more cases of this disease. And as we've got more and more cases, we've started to see some strange presentations of COVID-19, some rarer things that haven't necessarily been associated with respiratory viruses before. So for instance, children seem to be developing strange feet conditions, some inflammation on their feet. This loss of taste and smell for a week or so is quite a strange manifestation. And there's some strange manifestations in blood clotting and things like that. So there's quite a lot to learn about the pathogenesis of this virus over time. Now, while there's a broad spectrum of symptoms associated with COVID-19, it still seems to be tracking that the people who develop the most severe symptoms are those with underlying health conditions. So the elderly are still disproportionately developing severe disease, as are people with things like diabetes or high blood pressure or other lung problems, so chronic lung disease or people with damaged lungs from, say, smoking or air pollution. So it looks like the most severe cases are still associated with these underlying comorbidities. And so that just brings me to a little transition slide here to just reiterate some of the questions I've kind of alluded to while going through my slides. Some of the things we're thinking about regarding the current situation, such as the real number of cases, the test issues with testing, and this chance of seasonality and second waves, and how to manage those kind of things. But I'm using this as my little transition slide to spend a couple of minutes telling you about the work we've been doing here in the Freeman Lab in Baltimore. It's at the University of Maryland School of Medicine, before I then open up the floor for the Q&A. So please keep putting questions into the chat and I'll tackle them all at the end. So as I think everyone is now painfully aware of, we don't have any vaccines or antiviral drugs to treat coronaviruses, be it this one or SARS-1 or MERS. And this is actually a broad feature of a lot of viral infections. We do lack any real good countermeasures. However, there are many things that we can research and look into. And one of these is the idea of repurposing FDA-approved drugs, which is one of the focuses I've been putting my time into. So this idea here is that there are a lot of drugs approved by the FDA for treatment of various conditions, be that cancer or diabetes or high blood pressure or stroke or depression and so on and so forth. And what you find in the lab when you look at these drugs is that you can find a lot of them actually have antiviral activity. So for example, back in 2014, the Freeman Lab performed this study to look to see whether FDA drugs had antiviral activity against the two coronaviruses we cared about back then, which was SARS and MERS. So here they took a library of 290 FDA-approved drugs and found that 27 of those were capable of inhibiting both SARS and MERS infections in the lab. So this was promising. So from that, we shortened the list down to 20 and looked to see whether any of those were capable of also inhibiting SARS-2, as that would suggest that they have broad anti-coronaviral activity, which means they could be really beneficial for this current outbreak and potentially for future coronavirus outbreaks. So we wanted to do this as quickly as possible, but also with as much scientific rigor as was possible. So we set up the infection, we did everything in triplicate, we repeated it all 3 times, and we did it at 2 different levels of virus infection. And we set up the assay to look to see if we could protect our cells from dying. So when working in the lab with SARS-2, if you infect cells, those cells die over time as the virus replicates and grows and it kills the cells. So we were looking for drugs here that could protect our cells from dying. From all that work, we can produce data that looks like this. So this is all 20 of the drugs we worked with. Now what you're looking at here in blue is the percentage of inhibition. So this is an inverse of the amount of cell survival. So 0% inhibition, this is when the virus can just wreak havoc and kill all the cells. And when getting close to 100% or at 100% inhibition, this is when there is no growth of the virus and the cells grow as happily as if they were uninfected. So we're looking for drugs that can give a very good level of inhibition. But we're also looking for drugs that aren't directly toxic to the cells. If you add too much drug to the cells, you can kill the cells by toxicity. So we're looking for a good separation between blue and red. If you take something like anisomycin at the top row in the middle, this is obviously not a great one for us to be working with, as when we use this drug at any of the concentrations in these experiments, it was just killing our cells. So we could learn nothing about how the virus was replicating in those cells. If you take amidiaquin on the top left graph, you can see we achieve a good separation between blue and red, so this is a good candidate. we're getting close to 100% inhibition at a level that's around, well, a little bit over 0% cytotoxicity, so death of the cells. Now, I just want to draw your attention to two of the drugs on here in particular, because we followed up directly on these because they were making the news because of certain people talking about them. So these are chloroquine and hydroxychloroquine. So we see in this assay that treatment with both of these drugs is capable of protecting our cells from being killed by SARS coronavirus 2 infection. And we also see that treatment with these drugs is capable of directly inhibiting replication of the virus. So here in black, you're looking at control cells that were not treated with drug and the amount of virus that came out of those cells. And then going to the right in each graph is just increasing concentrations of drug treatment. And I'd like to point out that this is a logarithmic graph. So if you take chloroquine at 50 micromolar, the highest concentration, so the furthest to the right, this doesn't look like a massive drop on the graph, but that is about a 1 log drop, meaning a roughly 90% reduction in the amount of infectious virus coming out of the cells. And if you take hydroxychloroquine at the highest concentration, so the left-hand graph on the furthest right, that's over a 2 log drop, so over a 99% reduction in the amount of infectious virus. So these drugs do work at inhibiting replication of this virus. So from there, we've just gone on and screened more and more drugs. We've done well over 600 drugs now in the lab, and we're looking to expand even further, expanding our capabilities and our capacity, and start to do combinations and try and find really good ways to inhibit replication of this virus. And then as we develop small animal models, so mouse models, we're going to look to see what works in mice and then really try and push those into clinical trials with the companies we're working with. So along with the work on drugs and the idea of repurposing drugs, we've also been doing other work that I'm just going to touch on for 2 slides. So for example, we've been testing monoclonal antibodies, which may be protective and could be potentially used in patients. For example, with Regeneron, we've done some work with some of their monoclonal antibodies, and they're going to be starting clinical trials in June based on the results of some of the work we've done here. We've also been working on vaccines as well. So in collaboration with Novavax, we've been testing one of their vaccine approaches, and based on the results we've provided them, they're looking to start clinical trials in May. So this is really exciting for us that we are helping move things into patients, and we can only hope that that then has broad implications and that they work. But right now it's obviously too early to know because we're still waiting for them to be trialed. And that's all I want to say for tonight on my side before I go into doing the Q&A. Again, I've just put up a few of these remaining questions, some sort of ideas of the kind of things we're thinking about, the kind of things that maybe you'd want to think about and you can ask, just as a little prompt and a transition slide as I move through the last couple of slides to just do some acknowledgements. So I just absolutely need to acknowledge the lab. So this is the Freeman lab. Matt Freeman is the boss, and this is the rest of us that work in the lab. It's a wonderful place to work. This was an acknowledgement slide that Matt made, and I stole it. I wasn't super keen on his idea of making gifs of us that makes us look like we're Harry Potter photos, hence why I'm saying nope in my image on the left-hand side. But he liked it so much I thought I'd use it. So the lab is Matt, the boss, myself, the postdoc Stuart. Then we've got Rob and Jimmy as 2 PhD students, and Crystal and Holly as our technicians. And these are all the companies that are funding us, that we're working in collaboration with, testing potential drugs, testing antibodies and vaccine strategies, and some governmental agencies on here and all that. So there's a lot of people who are giving us money to work, and reagents and things like that to work with to try and combat this virus. And finally, I'd just like to again say thank you to the hosts. So Brewing Up Science, of course, thank you, Jackie, for putting this together, and all of our co-hosting breweries and distillery. As I said, please, if you can, support them, and as soon as we open back up, get over to their wonderful drinking establishments and have a beer or some whiskey. They're wonderful places to go. Okay, so with that, I guess I'll go into the question section of this, the Q&A, which I'm hoping will be maybe the thing of most value. I do think we're a little bit time limited on this Zoom call, so I will go through some of these very fast. If you want more detail, please reach out to me on Twitter or the YouTube channel when we post this up there, just so I can tackle some of the questions I may end up having to miss or not answer with as much detail just because of trying to get through as many as possible. So with that, the first question up in the chat is from Jenny saying, why was there early speculation that this wasn't a big deal? So I guess at least for me, and why I, at the early stage of January, thought this wouldn't be a big deal, I guess optimism, part of it. The other part of it was that, I mean, the precedence from SARS and MERS was that maybe it wouldn't be. SARS spread around the world in 8 months and caused 8,000 cases. MERS has been spreading for 8 years and has caused 2,500 cases. So the fact this virus has caused over 3 million cases in 4 months is pretty crazy. So I guess I was hoping it would be more like the other coronaviruses. I obviously did have a fear that there could be something like this. I think, as I said while I was doing the slides, part of why I came to a coronavirus lab was because there was always a thought that something like this could happen. But I think I was downplaying it in those early stages because I didn't want to think it actually would. Obviously, we rapidly understood that it was going to be a bigger deal than initially thought. So next up, question, Anne-Marie. Is it possible that the first case was here prior to the 20th of January? Was that just the first diagnosed case? I think absolutely. As I alluded to when I was talking about the number of cases and the case fatality rate, testing is a big limitation right now. We are not testing enough, or we have not tested enough. And so I really do think that there are cases that will have occurred before that's first detected or a first official case. I even know anecdotally people who talk about having lost the sense of taste and smell and had low-grade fever and cough and things like that in the early stages of January. So just myself, I have anecdotal evidence, and I'm sure various other people do as well. So I do think that the first case was prior to the 20th, but that was the first officially diagnosed case. Okay, so a question up from Jeff and Beth together. Do we have a sense of the percentage of people who are asymptomatic? So perfect follow on from that last question. We really don't, because we're just not doing enough testing. We need better serology testing. So this is the test that determines who's been infected because they produced antibodies. The other test is a test for RNA, so looking for the viral genome, an RT-PCR test, which detects active cases. So we aren't doing enough of either testing, and we don't have good enough serology tests yet, because even something like a 5% false positive rate, which seems sort of the best level at the minute. Obviously, the higher the false positives, the worse. So 5% is kind of our best at the minute. We don't have a good enough one. We need that to be better to really get a sense of the true number of cases, and we just don't have enough of that testing, and we don't have enough testing of people who are actively infected. So right now we really don't have a true idea of the percentage of asymptomatic people. I think that will be something that's done in follow-up studies when we do much broader serology testing of places once it all calms down and we can just study this for what it was, not have to sort of make sure our hospitals aren't being overwhelmed. So the next couple of questions that have come up in the chat here is two pretty similar ones from Lewis and Johnny, asking about the possibility of a second wave. And I do think that there could be a second wave. I don't want to go into the politics. I want to focus on the science, but I do think there are places that are opening up too soon. And this is going to be a perfect indication of whether this virus is going to have a resurgence once we stop doing social distancing measures. As an example of how that can occur, let me just use Spanish influenza from 1918. So two often used examples with Spanish influenza are Philadelphia and St. Louis. So it's around Labor Day. So I always mix up Labor Day and Memorial Day. In September, Labor Day, I think. That was around the time that there was the second wave of Spanish influenza was arriving in America. And in Philadelphia, they had a mass parade for the holiday where 200,000 people attended. And they had a huge spike in deaths per capita from influenza shortly after that, and from other conditions, because their hospital system became overwhelmed. St. Louis, conversely, locked down. They closed schools, they stopped mass gatherings, and all those kind of things that we're doing now, as soon as they got their first case of influenza. And they flattened the curve. Social distancing worked. But it was found that once they stopped all of those measures, they did have a spike in cases that occurred. Not a true second wave, but just a demonstration that things can come back. Now, the other thing that rolls into the idea of the second wave is seasonality. And seasonality is well established for flu. So flu season is a thing. You get more flu cases in the winter because the virus transmits better generally. With coronaviruses, it's a little bit unclear about whether there's true seasonality. So those common cold coronaviruses that spread every winter, it's possible that they only really spread in the winter because that's when people are susceptible, because you only really develop an antibody response that protects you against those viruses for about a year or two, and then you become susceptible again. So maybe that's more about the susceptible population, not an environmental seasonality thing, as is kind of seen with flu. With SARS, that virus just didn't spread long enough to know about seasonality. It emerged in November and it disappeared in July. So you can't say anything about seasonality because we didn't have long enough. With MERS, most cases are occurring in the Middle East, and we've been having sporadic cases there for 8 years. And it's obviously very hot in the Middle East. But the virus doesn't transmit very well, so maybe it is sensitive to temperature. So maybe coronaviruses are sensitive and spread better in colder temperatures. So maybe we will see seasonality or a decline in summer, and then a second wave in the fall and winter. Hard to know right now, basically. I do think if we relax social distancing too soon, though, that will cause its own second wave. Whether we see a seasonality second wave, that remains to be seen. So next up, question from Holly. I've heard there are multiple strains. Is this true? And if so, how is that being addressed in research and study? So there was an early suggestion of strains, and I think they were called the DNL strain or something like that. The reason I don't know what they were called precisely is because that was rapidly debunked. We don't really have evidence of multiple strains. There are mutations occurring, but it's not really causing many big differences to the viruses that are spreading in humans. So most of the viruses that were first isolated in China and the very first cases and the ones now are very genetically similar. Coronaviruses don't mutate very rapidly as a general point compared to other RNA viruses, I should say. So if you take something like flu, this mutates very rapidly, which is why we need seasonal vaccination. Coronaviruses, conversely, do not mutate at the same rate, and that's because they can proofread. So mutations occur when viruses are trying to copy their or are copying their genome to make more virus particles and spread infection. And errors get made, and that's mutation. Coronaviruses can proofread, so they can check and see if they've made mistakes and correct those, and so they don't mutate very rapidly. So we aren't really seeing any evidence of multiple strains. So Collins asked, when you see the differences in countries' reaction speed and preparedness, what in your approximation is necessary to help so that countries do not have to shut down? That's a nice question. So I think it's testing. Testing is the most important, but I also think contact tracing is going to play a role. So hopefully we're going to learn from the errors from this first wave, if indeed we have to deal with a second wave, so that we don't have to shut down, or at least shut down so extensively. So let me use the example of South Korea. South Korea suffered pretty severe outbreaks of SARS and MERS, and as such enacted systems to allow for pretty extreme contact tracing. So it's possible for the South Korean authorities to look into people's credit card records and phone records to see where they've been. So if someone tests positive, the authorities can look at all the places they've been and work out all the people they've come into contact with. So let me use an example around the Brewing Up Science thing we're doing. If someone were to go to a live Brewing Up Science in a brewery who had this virus and tested positive for it in South Korea, it would be possible to then look at their credit card records, see that they went to one of the wonderful breweries that are hosting Brewing Up Science, see all the other people who were there, and then offer those people tests. And South Korea was able to do that level of testing. I believe the number is something like 55 tests per one positive case in South Korea. By comparison, America, I think, is about 5, and the UK is about 3 tests per positive case. So having that level of testing allows you to really work out who's infected and to really lock that down by putting those people into quarantine and testing until you just and testing and quarantining until you block that transmission of the virus. So if we can start to have systems like that, that would allow us to reduce the level or the degree of shutdown. Now, I am not sure I'd want to be somewhere with that level of surveillance, that level of potential privacy issues about where your phone has been and where you've been spending money and all those kind of things. But just having systems in place where healthcare workers can talk to you about where have you been, and it can be done verbally, and then people who you've been in contact with in bars or breweries and things like that, or restaurants, wherever, they can be offered tests. So I think testing is the most important, and contact tracing is going to be very important for having a rapid response and hopefully limiting shutdowns in the future. Okay, so next question up is from Russell. Do you think that the development of a vaccine is possible? I thought you mentioned that there haven't been vaccines for other coronaviruses. Why would there be a better chance for this one? So, to put it bluntly, I think there's a better chance for this one because there's more money being put into it and there's more impetus. So if you take the common cold coronaviruses that we don't have any kind of vaccination for, it's because there's no impetus to. It's hard enough to get people to take the seasonal flu vaccine, so which does cause severe disease and hospitalizes people. So there is no impetus. Sorry, there is no impetus for people to make a vaccine to a common cold. Very, very few people get hospitalized by it. It's something you just deal with and often don't even have to take off work. So there's no real drive to produce a vaccine to those coronaviruses. But in terms of the more severe coronaviruses, so SARS-1 and MERS, we just weren't able to produce a vaccine in time. So for producing a vaccine to these viruses, you need enough spreading cases. We can't infect people with these viruses because they're too lethal. So the way that you have to work out if a vaccine is working is by having a vaccinated population and a placebo control population, and then seeing who develops more instances of infection. And you can't obviously push the odds of infection by challenging people because that's just ethically not doable. So you need the virus to be spreading actively, and you need time to see whether there is indeed protection in your vaccine cohort. So with SARS, that virus only spreaded for 8 months and caused 8,000 cases and then disappeared. So we didn't have time or potentially enough cases to get a vaccine going. With MERS, that virus has spread for 8 years, but it's only caused 2,500 cases. So there hasn't been enough spread to work out whether any vaccine approach was going to work. Why I think it will be different for this one, because I really do think we will get a vaccine, is this virus is going, it's here, and we've really got to tackle it. So there is huge impetus, there's a huge amount of money, there's a huge amount of interest, and the virus is rapidly spreading around the world. So we have the chance to work out whether any vaccine is beneficial and, importantly, whether it's safe. So that's why I think it will be different this time. So we're getting close to running out of time here, so I'll just do a couple of quick questions that are in the chat. Sorry to everyone I've missed. Like I say, please reach out through the social media stuff if you have pressing questions. So I've got one from Brad. How was your day-to-day in the lab changed? Are you receiving new requests for collaboration? Absolutely. That collaborators slide I put up at the end of my presentation was only produced within the last month. We did not have that many people giving us money before. So there's a huge amount of extra collaboration going on because these viruses are high containment and only certain people in the world can work with them, of which we are. And because of all that, the day-to-day has definitely changed because I'm working much longer hours and I'm doing a lot more talking about all of this, of course. So I'm doing this presentation. I did one on Monday. I've got the YouTube channel, obviously, as is on the slides. As I sort of joked about, I was talking about SARS-1 coronavirus back at the start of January with my now girlfriend. So I was talking about coronavirus whenever I could before, but now people actually want to hear about it. So the whole day-to-day has changed a lot. It is very weird that we're the only people in the building, though. So the whole day-to-day lab life, it's very strange to just be around the same 6 people the whole time and see no one else around the building. and hopefully soon enough everyone else can come back to work. Okay, so I'll just do I'll just do a couple of quick ones to finish off on. So from Sean, is there a recent preprint paper that a preprint or paper that you have found very interesting, and why? So the one I'd just like to highlight is one that suggested that saliva samples might be a better source of material to diagnose people as having this virus. There may be more virus to detect in saliva. Now, the reason I think this is really interesting, if it holds true, is because testing is a big problem, as I've been talking about. And the tests are not all that easy to do. Right now, you have to stick a swab up someone's nose, basically up into their brain. Um, I exaggerate slightly, of course, but it's hard to get a good sample. Well, you can get good samples, but if you're taking thousands of them, it's possible that you don't get it into the right area. I don't mean that as a criticism of any healthcare workers, of course, but it is a thing that can happen. So it's sometimes hard to get good samples, and it's also very uncomfortable. Apparently, I've not had one myself, but I hear it's very uncomfortable, and it can make you cough and sneeze and things like that. So that's putting people at danger. The healthcare workers that are taking those samples are at danger of being affected if they get coughed and sneezed on because they're taking the sample. So if you can get good samples from saliva, that's really good. And if it really holds up that this is a better source, you can start offering at-home testing. You can send out spit kits and people can just spit in it at home and find out if they've been infected. So then you don't have such chains of transmission. People can stay isolated at home and find out if they need to stay isolated at home or if they can go back out. So I think that could be a real game changer, which is why I'll highlight that one. Okay, so we're very close to the end of the Zoom time, so I'm just going to wrap up on the last question, which has come from Sean again, just because I think it's a funny one for me to stop. So in this question, Sean has asked, for people who aren't looking at the chat, and for, I guess, the people who might watch this on the recording later, I've heard that bleach can get rid of this thing in like a minute. Should I drink bleach? No, please do not drink bleach, Sean, or anyone else. Bleach can kill the virus, but it will kill you just as quickly. And while I'm doing public service announcements, also, please don't run with scissors, because apparently we need to say things like that nowadays. Anyway, we're right close to the end of the Zoom time, so I'm going to wrap up there. Thank you everyone for tuning in. Like I say, please, if you have other questions that I haven't been able to tackle or haven't given good answers to, please reach out on the social medias that I've put up at the top. Very happy to talk if you've not noticed, because we've been doing this for a little while and I've basically been monologuing. So thank you for tuning in. Thank you to Jackie for organising it. I really, really enjoyed my first Brewing Up Science session back in November, and I've really enjoyed this one. So thank you, everyone. Stay safe, wash your hands, all those good things, and don't drink bleach.